Welcome back, ladies and gentlemen. In this final video of chapter 6.6, we are going to define de Moivre's theorem and utilize it in an example here. Now, de Moivre's theorem is something that just really is convenient more than anything else. I am not going to utilize this video to prove de Moivre's theorem. There are plenty of videos out there, and there is access in just about every textbook that has pre-calculus in it that has de Moivre's theorem and a proof for it. But just kind of take our word for it that right now, honestly, it is a very convenient theorem for us. Reason being is because if you think just about how, I guess, inconvenient, right, it would be to go ahead and to multiply a large exponent of complex numbers, right? So you think about what I mean by that. I say, well, let's say, for instance, you had a plus bi, and you wanted to go ahead and do this in a way where you had to raise that, let's say, to the 8th exponent. Like, as of right now, all you really know how to do is to literally write out a plus bi 8 different times, so on and so forth, to 8 different times. And that would not be fun, right? At minimum, maybe you could sit there and go ahead and understand that if you did 2 of them using some of our complex number multiplication rules that we just talked about, that would be a little bit easier. But still, the reality is that it'd be very inconvenient to do. But then we also know that we could rewrite a plus bi as the modulus times the cosine of the direction angle plus I times the sine of that angle. So, when you think about it this way, you actually give yourselves an opportunity to use de Moivre's theorem. And so de Moivre's theorem ends up basically giving us an idea that, well, all right, I don't necessarily have all of this, but I can rewrite any of my a plus bi's in this form here. And so if that's the case, de Moivre's theorem allows us to utilize this positive n integer in a little bit of a different way. As you can see, we can raise the modulus to that nth degree, and we can go ahead and multiply the angles inside by that positive integer n, and that is what de Moivre's theorem allows us to do. So let's see it in application now. So I want to go ahead and take 1 plus I times the square root of 3 to the 3rd power. So again, we got to kind of think about this in terms of what is the polar form of this complex number going to be. And so we have z as 1 plus, and I like putting square root of 3, honestly. I like keeping it how it is there when we're talking about I don't like really mixing them up. So if that's our standard form, we need to go ahead and find out what that polar form is going to be. And first and foremost, we're going to have to find what that modulus of the theorem is, or of the complex number is. So r is going to be 1 squared plus the square root of 3 squared. So you get the square root of 4, so it will equal 2. And so now I can understand that z is really equal to 2 times the cosine theta plus I times the sine of theta. But I have to figure out what that theta is before I can do anything with de Moivre's theorem. So let's keep in mind, where are we? Well, we're going to be with 1 and a square root of 3, so we're in quadrant 1. So we can think about, and our modulus is 2. So we have cosine theta ends up being 1/2. So I like using cosine when it's in quadrant 1. So cosine is going to be 1/2 at pi thirds. So I can rewrite my z as cosine of pi thirds plus I times sine of pi thirds, all multiplied by 2. And then we can go ahead and utilize de Moivre's theorem at this point. Since now we have it in our polar form, we can go ahead and use de Moivre's theorem. So all of this was being raised to the 3rd power in the very beginning. So I can take z cubed, and that would be 2 to the 3rd power times cosine of 3 times pi thirds plus I times the sine of 3 times pi thirds. And so then we end up getting 2 to the 3rd power. That's an easy one to do, is 8. 3's would cancel. And so then we get the cosine of pi plus the I times the sine of pi. And, well, cosine of pi is just going to be a -1. And sine of pi is 0, so the whole imaginary number is going to be gone by the wayside. So we have 8 times a -1, which just gives me 8. And that would be what z to the third power, or what 1 plus I root 3 to the third power would be using de Moivre's theorem. So it's kind of just recap. You want to make sure that you first and foremost can identify what the modulus and the angle are going to be. Turn that guy into polar form, and then you can utilize de Moivre's theorem with no problem at all.